Now I will give an overview of what statistical mechanics is. Let us consider a system, and let's say this system is isolated, so it cannot exchange energy or particles with the surrounding. And in thermodynamics, we talk in terms of macroscopic properties. Let's say like temperature, volume, energy, entropy, pressure, and so on. And we try to find the equation of state. Once we have the equation of state, then we can find the macroscopic properties. Now, in the same system, if I try to see in microscopic scale, then let's say this is the ith particle. Now, this particle will have some position, it will have some linear momentum, it will have some velocity, and it will have some kinetic energy, and so on. So, these are the microscopic properties. Now, we are talking of the same system. On one side, we are talking in macroscopic scale, and on other side, we are talking in microscopic scale. So, since it is the same system, there should be some correlation between the microscopic property and the macroscopic properties. And that is what statistical mechanics does. Now, let us consider a system here, the same system. So, for this system, let's say the macroscopic properties are defined by E, V, and N, energy, volume, and number of particles. Now, in this system, the molecules are constantly moving. Now, let us try to take a snapshot at another time, let's say like this. Here, the position of the particles are different, but the macro state remains the same. But the micro state are different. So I'll call this one as micro state 1, and this one I'll call as micro state 2. So now we are having two systems having same macro state but different micro state. So like this, we can have many identical systems with the same macro state but different micro state. So we can have many numbers, and this is what we call as the ensemble. In ensemble, what we do is we find the average value. To be more specific, it is the weighted average of microscopic properties and try to correlate with the macroscopic properties. Now, there are three ensemble theories. One is microcanonical. Second is canonical. And the third type is grand canonical. These are the three types of ensemble. Microcanonical ensemble, where the system is isolated. Canonical ensemble, where the system is kept in a thermal bath, so it can exchange energy but not the particle. In grand canonical, it can exchange both energy as well as particles. Now, from microcanonical ensemble, the energy, volume, and number of particles will remain constant since it is isolated. But in the case of canonical, since energy is exchanged, it no longer remains constant. Rather, the temperature, volume, and number of particles will remain constant. In the case of grand canonical, temperature, volume will remain constant, but not the number of particles, because now the particle is exchanged. So here we use chemical potential. Chemical potential, we can say it's a kind of a resistance of the system in adding new particle to the system. Now, in this video series, we'll be focusing only on canonical ensemble. in the question, whenever it is mentioned like the temperature, the system is kept at a particular temperature T, or let's say the system is in contact with a thermal bath at temperature T, then it is referring to the canonical ensemble. Now in canonical ensemble, the probability for the particle to be in a particular energy level, let's say epsilon I, this is given by exponential minus epsilon I beta divided by summation of e to the power minus I epsilon I beta. Now beta here refers to 1 by Boltzmann constant into T, and the summation runs for all the possible energies. Now suppose if the system has degeneracy, in that case there will be an additional factor here, Gi, which refers to the degeneracy. Now the term in the denominator is what we refer to as the partition function. If we know partition function of a particular system, then we can find out all the thermodynamic variables. Now we will discuss how to calculate the thermodynamic variables from partition function. We know the probability formula, so it is Gi e to the power minus epsilon I beta divided by summation of Gi e to the power minus epsilon I beta. Now the partition function is generally denoted by the capital letter Z, so we can write like this: epsilon I beta divided by Z. Now if we know this probability distribution, we can find the average value of any observables. So if I want to find the average value of the observable f, then we can use the formula from statistics. So it will be summation fi Gi e to the power minus epsilon I betas divided by Z. So using this formula, we can find the average energy. So it will be summation epsilon I Gi e to the power minus epsilon I beta divided by Z. So this formula is useful when we know the probability distribution. Suppose we don't know the probability distribution, but the partition function is given. In that case, the average energy is given by the minus of partial derivative of log of partition function with respect to beta. Now we know that beta is equal to 1 by kBt, so we can express this partial derivative in terms of temperature also. So it will be kT square del of log of Z with respect to temperature. Now the average pressure is given by 1 by beta partial derivative of log and Z with respect to volume. Similarly, we have the average chemical potential is equal to minus 1 by beta log Z with respect to N. Now free energy. In this video series, I'm using F as the notation. So F is given by the relation minus kBt log of Z. But this relation can also be written like this. We know that F is equal to U minus Ts. So it will be U average value U, that is average energy, minus T into average entropy. Now using this relation, we can express entropy as average entropy as kB T log of, no, it should be like this. 1 second. So it will be kBt log of Z minus 1 by T partial derivative of log of partition function with respect to beta. So these are the formulas, and now let us try to solve the previous year questions. In this question, the partition function is given and we are told to find the temperature dependence of specific heat, and in the second part we have to find the pressure. Whenever specific heat is asked, you need to find the average energy. So average energy, we know kBT square partial derivative of log n z. So if I substitute this, then you'll have pi square V kb t cube divided by 45 h bar cube c cube. Now in this term, these are constant, and we have t cube. Sorry, this should be t, derivative with respect to t. So we have t cube here. So if we differentiate, then we'll get t square. And with this t square, it will give t to the power 4. And other terms are constant. So what can I do is I can replace all the constant by say C1, and you'll get t to the power 4. Once you get the average energy, you can calculate the specific heat using this relation. So if I differentiate this, I'll get 4C1T to the power 3. So specific heat is directly proportional to T cube. So if we come back to the plot here, then this plot will be a cubic function. In the second part of the question, we have to find the pressure, average pressure. So average pressure is equal to 1 by beta differentiation of log of z with respect to volume. Now, if you see the log n z expression, we have a v term here. So this v term will differentiate and it will give 1, and the other terms are constant. So I can directly write the answer here. So it will be 1 by beta pi square kb t cube divided by 45 h bar cube c cube. Now beta is equal to 1 by kbt, so I can substitute that. So it will be pi squared, so this kbt will become to the power 4 divided by 45 h bar cube c cube. So option C is the correct answer. In this question, the partition function is given and we are told to find the heat capacity of this ensemble at this temperature, and they have already given the expression of the heat capacity, that is x and kb, and we have to find the value of x. So since heat capacity is x, we need to find the average energy. So the average energy is given by kbt square partial derivative of log of z with respect to temperature. So if I substitute, then I'll get n kbt square, then the derivative of log of 2 cos hyperbolic epsilon kbt. Now you can pause the video and do this differentiation. It's very easy differentiation, and I'll write a final expression here. So it will be minus n epsilon tan hyperbolic of epsilon by kbt. So now we have got the average energy. So the heat capacity will be given by the derivative of the average energy with respect to temperature. Now you can substitute this. So it will be minus n epsilon partial derivative of tan hyperbolic epsilon kbt. So if you differentiate this, then you'll get the expression C is equal to n epsilon square kBt square sec square hyperbolic sec square hyperbolic epsilon by kBt. Now this is the expression of the specific heat, and in the question it is given that the specific heat is evaluated at T equals epsilon by kBt. Now if you substitute this T here, then you'll get C is equal to, and here also you have to substitute because here is one temperature T square term. So you'll get n kb sec hyperbolic square 1. So if you compare this expression and this expression, then x is equal to sec hyperbolic square 1. So this is the answer. When we are solving the numericals for partition function from energy levels, we need to understand certain concepts, like whether the given particles are distinguishable or whether it is indistinguishable. Let us take two particles of the same type, but here these two particles can be distinguished because one is blue in color and the other one is red in color. Now if we try to place these two particles in a two energy level system, then we can place it like this. Now if I interchange these two particles, then I'll be getting a configuration like this. Now if we compare these two configurations, they are different. So whenever it is mentioned that the particles are distinguishable, then we have to find all the possible configurations. Sometimes they will have different configuration, but the total energy will be the same. In that case, we have to take care of the degeneracy. For indistinguishable particles, we can take two electrons. Let us try to place this electron in the two energy level. So in this configuration, now we will interchange the two electrons. Then we'll get a configuration like this. Now if we compare the two configurations, they are the same. So it is not giving any new microstate. Another concept which we need to take care is, when it is said it's a quantum particles, then we have to identify whether it is fermions or bosons. The basic difference between fermions and bosons is, fermions are odd half integral spin particles, and bosons, they are integral spin particles. So if it is mentioned that the particles are fermions, then we have to make sure that it does not violate the Pauli exclusion principle. That is, no two fermions can have the same quantum state. Here it is said two atoms can be placed in three quantum states, 0, epsilon and 2 epsilon. And the system is in equilibrium at temperature T. So it is a canonical ensemble. And we are asked to find the partition function for classical distinguishable, classical indistinguishable, then for fermions and bosons. So first we will try to find for classical distinguishable. Now since the particles are distinguishable, we have to find the different combinations that are possible. So we have three energy levels, 0, epsilon and 2 epsilon. So I'll draw a table here, 0, epsilon, 2 epsilon, and let this be the total energy. So, and I'll call the two atoms as A and B. So I can place AB here. So the total energy will be 0. Then I can place A here, B here. It will be epsilon. Now if I interchange this AB, we are getting the same energy but different configuration. So there is a degeneracy. Now we can have A here, B here. So this will give 2 epsilon. Now I can again interchange this A and B. So 2 epsilon. And we can have both AB here. So this will also give 2 epsilon. Then we can have A here, B here. That is 3 epsilon. Again, now I can interchange A and B. This will also give me 3 epsilon. And finally, I can place A, B both at the highest energy level, and this will give me 4 epsilon. Now let us check the degeneracy. Here we have a degeneracy of 2. Here we have degeneracy of 3. Here 2. And so now we have all the possible combination. Now we can write the partition function. So Z is equal to summation gi e to the power minus epsilon I beta. So if I write, then the first term will be minus 0. Second term, degeneracy of 2, so minus epsilon beta. Then third term has degeneracy of 3, so 2 epsilon beta. Then we have degeneracy of 2 epsilon beta plus e to the power minus 4 epsilon beta. So the final answer is 1 plus 2 e to the power minus epsilon beta plus 3 e to the power minus 2 epsilon beta plus 2 e to the power minus 3 epsilon beta and e to the power minus 4 epsilon beta. So this is the partition function for the classical distinguishable. Now let us try to find for case 2, that is classical indistinguishable. Whenever this case comes, the trick is first you find for a single particle. So there are 2 atoms. Now I'll try to find the partition function for single atom. Now for single atom, in one case it can, okay, so this is epsilon, this is 0, epsilon and 2 epsilon. So we can place the particle here. In second case, we can place the particle here. In the third case, we can place the particle here. So these are the possible configuration for a single particle. So if I write the partition function for this, it will be e to the power minus 0 plus e to the power minus epsilon beta plus e to the power minus 2 epsilon beta. So this gives 1 plus e to the power minus epsilon beta plus e to the power minus 2 epsilon beta. Once we find for a single particle, then for n particle, we can generalize by using this formula. Now, here we have to divide by n factorial because since it is indistinguishable, the interchange of these particles or atoms will not create any new states. So that's why this n factorial comes. So for this particular case, the final partition function will be z1 to the power 2. That is, since there are 2 atoms, then we have to divide it by 2 factorial. So it will be 1 by 2 into 1 plus e to the power minus epsilon beta plus e to the power minus 2 epsilon beta. So this is the final answer. Now let us calculate for the case of fermions. Now fermions, they are indistinguishable and they obey Pauli exclusion principle. Now in the question, it is given that the energy levels are quantum states. So if I put one fermions here, then we cannot put another fermions here. If we put here, then both the 2 fermions will be having the same quantum states. That is, it will violate the Pauli exclusion principle. So using this concept, let us try to find the possible configuration. So if I put A here, say I will call both the atom sets as A and A since it is identical. So if I put a here, then I have to put another a, so it will give epsilon. Then I can put one a here, then I can put another a, so it will be 2 epsilon. Now see, if I interchange this, it will not give any identical states. Now another possible configuration is a here and a here, so it will be 3 epsilon. Now these are the 3 possible configuration. So I can write the partition function, so it will be e to the power minus epsilon b plus e to the power minus 2 epsilon beta plus e to the power minus 3 epsilon beta. So this is the partition function when it follows the Fermi-Dirac statistics. For the fourth case, that is when the 2 atoms follows the Bose-Einstein statistics. So bosons, they do not follow this Pauli exclusion principle. So if let's say I'll call it B, so the 2 atoms I'll call it B and B. So if one atom is there, then another atom can also be here because they are bosons. So using this concept, we can find a possible configuration. So both B and B can be here. So the total energy is 0. Then one B here, another B here. So it will be epsilon. Then we can have both the atoms here. It will be 2 epsilon. So then we can place one here and another here. So this is giving 2 epsilon. Now we can see that there is a degeneracy because both of them are giving 2 epsilon, but their configurations are different. Then we can have one here, another here. So this will give a total of 3 epsilon. And finally, we can place both the bosons here. So it will have 4 epsilon. So these are the possible configuration, and we can see there is a degeneracy of 2. So now we can write the partition function. So z will be equal to e to the power minus 0 plus e to the power minus epsilon beta plus 2, because there is a degeneracy, into e to the power minus 2 epsilon beta plus e to the power minus 3 epsilon beta plus e to the power minus 4 epsilon beta. So the final answer is 1 plus e to the power minus epsilon beta plus 2 e to the power minus 2 epsilon beta plus e to the power minus 3 epsilon beta, and the last term. So this is the answer for the Bose-Einstein statistics, if the 2 atoms are following Bose-Einstein statistics. Here, the system consists of 3 energy levels, 0, epsilon, and 2 epsilon. And the epsilon energy level is twofold, and the other 2 are non-degenerate. So compared to the previous questions, here the degeneracy information is given. So we have 3 energy levels. One is 0, epsilon, and 2 epsilon. And they have given the degeneracy here. So this is twofold, and the other 2 is non-degenerate. Now we can straight away write the partition function, that is summation gi e to the power minus epsilon I beta. So we have e to the power minus 0 plus 2 e to the power minus epsilon beta plus e to the power minus 2 epsilon beta. So 1 plus 2 e to the power minus epsilon beta plus e to the power minus 2 epsilon beta. Now, this expression we can simplify using the a plus b whole square formula. So this one we can write as 1 plus e to the power minus epsilon beta whole square. So option C is the correct answer. In this question, it's a system of two bosons and each can occupy any of the two energy level, 0 and epsilon. We have to find out the mean energy, that is the average energy. So since it is bosons, suppose if this energy level is 0 and epsilon, and since bosons are identical particles, so one configuration is both the bosons will be in the lower state. Another configuration is one in the lower state and one in the higher state. And in the third, we'll have both the bosons in the higher energy state. Now, please note here that if I enter in this second configuration, if I interchange the bosons, it is not giving any new state. So based on this, if I write the partition function, so z is equal to e to the power minus 0 beta plus e to the power. Here, in the second case, the total energy is epsilon, so minus epsilon beta plus e to the power minus 2 epsilon beta. So this is the expression of the partition function. Now, we have to calculate the average energy. So average energy, let's say U, this will be equal to summation epsilon I e to the power minus epsilon I beta divided by the partition function. So if you substitute for the first case, the energy is 0, so it will be 0 e to the power minus 0 beta plus, for the second case, it is epsilon e to the power minus epsilon beta plus, third case, 2 epsilon e to the power minus epsilon beta divided by the partition function. So it will be 1 plus e to the power minus epsilon beta plus e to the power minus 2 epsilon beta. So now we have the mean energy, that is epsilon e to the power minus epsilon beta plus 2 epsilon, this is beta, divided by the partition function. So this is the final answer. The difference between the previous questions is that here they are asking the mean energy. So first we have to calculate the partition function, then we will calculate the mean energy. Here we are given a system of n non-interacting distinguishable particle in a two energy level system, and it is at temperature T. So the energies are 0 and epsilon, and we have to find the population of the particles in the energy level epsilon at the high temperature limit. So these are the two energy levels. So we can write the partition function. So z is equal to e to the power minus 0 beta plus e to the power minus epsilon beta. So we have the partition function now. Now, we know that the probability for the particles to be in the epsilon energy level is given by e to the power minus epsilon beta divided by the partition function. This is the probability. Now, if I want to find the number of particles in epsilon energy level, this will be given by n into the probability. So we have n e to the power minus epsilon beta divided by 1 plus e to the power minus beta. So this gives the number of particles in epsilon energy level. But we are asked at the high temperature limit, that is kT is greater than epsilon. Now kT we can write as beta. So this expression is nothing but epsilon by epsilon into beta, it is less than 1. So what we can do is we can approximate this epsilon beta by 1 minus epsilon into beta. So if the temperature is very high, then we can make a more simplified approximation that is almost equal to 1. So using this simplified approximation, it will be equal to n into 1 divided by 1 plus 1. So this gives n by 2. So option A is the correct answer. Here we have to find the partition function of a two-level system given the Hamiltonian matrix. Now this question is different because here the energy values are not given. So what we have to do is we have to take this Hamiltonian matrix and the eigenvalue of this matrix will be the energy of the system. So I can find the eigenvalue. Let's say lambda is the eigenvalue. Then minus delta minus gamma minus lambda. This is equal to 0. So by using the characteristic equation, we can find eigenvalue. You can pause the video, solve it. Here I'm writing the final expression. So lambda, we have plus minus square root of gamma square plus delta square. So we have two energies. So one I'll denote it E1, it is gamma square plus delta square. Another I'll denote it as E2, it is minus of square root gamma square plus delta square. Now we have got the energies of the two-level system. Now let us calculate the partition function. So partition function Z is equal to e to the power minus beta into E1 plus e to the power minus beta into E2. Now let us substitute the expression of E1 and E2. So this will be e to the power minus beta square root of gamma square plus delta square plus e to the power. So this one will become positive. So beta into gamma square plus delta square. So this is the partition function, but the expression does not match with any of the option. So we can use the cos hyperbolic expression because this is e to the power minus x plus e to the power x. So z is equal to 2 cos hyperbolic beta square root of gamma square plus delta square. So this is the answer. So option B is the correct answer. Here we are given a three energy level system of energy G, 0, delta and 2 delta, and it is in thermal equilibrium, and we have to find the specific heat at high temperature limit. So first let us calculate the partition function. So this is 0, delta and 2 delta. So the partition function will be equal to e to the power minus 0 beta plus e to the power minus delta beta plus e to the power minus 2 delta beta. So we can simplify this and write the partition function. Now this numerical is a bit lengthy, but I will teach you two methods and how those methods can be implemented. So in method 1, we will use the free energy. So first we'll calculate the free energy. So free energy is minus the derivative of log z with respect to beta. Once you calculate this, you'll get an expression. Now in that expression, we have to apply this high temperature limit. So high temperature limit, it is given K beta T is much greater than delta. So you can rearrange this and write this condition, that is delta beta is much lesser than 1. So because of this condition, what you can do is you can approximate e to the power minus delta beta by the exponential expansion. So it will be 1 minus delta beta. Similarly, for e to the power minus 2 delta beta, you can approximate by 1 minus 2 delta beta. So when you substitute this approximation, you'll get a term like this with some constant and another constant divided by t. So from here you can find the temperature, the specific heat. So specific heat will be the partial derivative of average energy with respect to temperature, and you'll get 1 by t squared. This is one method. In another method, instead of using this instead of using the average energy, so you can use the free energy. So I'll call this as method 2. So free energy, also known as the Helmholtz energy, so you can calculate minus kBT log of Z. So you'll be getting some expression here. In that expression, you substitute this high temperature limit condition here. Once you get this expression after the substitution, you use the formula C is equal to minus T second order derivative of the average free energy with respect to temperature. So when you put this, you'll get the condition that it is proportional to 1 by t squared. So these are the two approaches of how to deal with this problem. Here we are given a 2-level system, and the ground state is non-degenerate and excited state is double degenerate. And we are given the energy difference, epsilon, and we have to find the specific heat at low temperature. Now, since the energy difference is epsilon, what we can do is we can consider the ground state to be 0 and excited state to be epsilon. And the ground state has 0 degeneracy and excited state has double degeneracy. So we can write the partition function. So it will be equal to 0 minus e to the power minus 0 beta plus e to the 2 times e to the power minus epsilon beta. So the partition function is 1 plus 2 e to the power epsilon beta. Now, here ultimately we have to find the specific heat. So we need to find the average energy. So average energy we can find using this relation, or here I'll do a different approach. We can use this relation also. Summation epsilon I e to the power minus epsilon I beta by Z. So here I'll use a different approach. So using this formula, we can write 0 into e to the power minus 0 beta plus. Here we have to include the degeneracy also. Here Gi should be here. So it will be 2 times epsilon e to the power epsilon beta divided by the partition function. So average energy is 2 epsilon e to the power minus epsilon beta 1 plus 2 e to the power minus epsilon beta. So now after getting the average energy, we can find the specific heat. So specific heat is given by the derivative of the average energy with respect to temperature. Now in this expression of energy, we can substitute. Without substitution also we can solve. So now you substitute the expression of average energy take the derivative with respect to temperature. How? Beta you have to substitute 1 by Boltzmann constant into temperature. Then you can pause the video, do the calculation. At the end, you'll get an expression like this. 2k epsilon by k beta t whole square e to the power minus epsilon beta divided by 1 plus 2 e to the power minus epsilon beta whole square. So you'll be getting an expression like this. Now, here in this expression, we have to incorporate the low temperature limit, that is epsilon beta is much greater than 1. So if that is the case, then this term we can approximate to 0. So the final expression will be 2 kb into epsilon beta whole square e to the power minus epsilon beta. So this is the final answer. This is a specific heat at low temperature limit, and if we see, then option C is the correct answer. This question is similar to the previous one, but here I will solve in a different approach by using trigonometry relation. So it's a two-level system consists having energy of plus minus E, and it is a non-interacting system kept at temperature T. So we have to find the specific heat at low temperature limit. So I'll call the lower one as minus E and the upper one as plus E. So the partition function is given by e to the power beta E plus e to the power minus beta E. So this expression I can write as 2 cos hyperbolic function beta E. Now we have to find the specific heat, so we need average energy. So average energy is minus of log of the partition function and with the partial derivative with respect to beta. So if I differentiate this, then you will get minus epsilon then hyperbolic E by kBt. So this is the average energy. Now once we know the average energy, we can find the specific heat, that is the derivative of the average energy with respect to temperature. So if I substitute this, it will be minus E then hyperbolic function E by kBt. So if you differentiate this, you'll get an expression E square divided by kBt square sec hyperbolic function square with an argument of E kBt. So this is the expression. Now in this expression, we have to substitute the low temperature limit condition. So what I'll do is I'll express the sec hyperbolic function in terms of exponential function. So C is equal to E square kBt square 1 by E to the power. So instead of kBt, I can substitute it with beta. Without substitution also it will work. So E by kBt plus exponential minus E by kBt whole square. Here we have to consider the low temperature limit. So low temperature means epsilon by kBT will be very large. So under this condition, what we can do is we can take this to be 0. So if I substitute this, then you'll get E squared by kBT square e to the power minus 2e by kBT. So this is the final answer. And I think it is matching with option B. Here we are given a 2 energy level system with energies epsilon and 2 epsilon. The lower energy has 4-fold degeneracy and upper has double degeneracy. And we are told to find the fraction of particles in the upper level. That is the probability of finding the particle in the upper level. So this is epsilon, this is 2 epsilon. So the degeneracy, the lower level has 4 and upper level has 2. So we can write the partition function. So it will be 4 times e to the power minus epsilon beta plus 2 into e to the power minus 2 epsilon beta. So the probability for the particle to be at high energy level, this is equal to 2 e to the power minus 2 epsilon beta divided by the partition function. That is this. So this expression we can rearrange. You can pause the video and simplify this expression. So you'll get 1 plus 2 e to the power epsilon beta plus 1. So option B is the correct answer.